Swayam Prabha. Digital India. Educated India.
So, materials informatics designates the digital revolution in material discovery or material development as such, and therefore, it is an important topic which has been introduced in this course. This is a futuristic topic, but it requires the basic understanding of materials as we have already done so far, and then we apply this understanding in order to make the material search very fast and new material development very fast. So, we will see how materials development, material selection transitions from traditional approach to a digital approach, and how material development is facilitated by materials informatics. Basically, we are talking about materials and informatics, and the flow of information is basically more rapid in the computational environment. So, we will see how it happens. So, you have two approaches. One is you have performance expectation, like let us say I want a material that should withstand high temperatures, it should have very good ductility, it should have a very low ductile brittle transition temperature. So, these are the performance requirements I have. So, basically the performance requirements translate to property requirements. Actually, I have pronounced the property requirements. So, the performance requirements of the material, a high temperature material which must withstand high temperatures, meaning it should be strong at high temperatures, it should be strong at low temperatures also, it should have good ductility at high temperature, good ductility at low temperatures also. So, there are certain requirements which translate into properties, and these properties can be achieved through the right kind of microstructure. So, you can plan for the microstructure and the crystallographic structure, and this structure has to be achieved using several processes. Now, these processes could be different manufacturing processes under room temperature conditions or high temperature conditions at different rates of straining, at different rates of deformation, or one can achieve it using a series of treatments like heat treatments, for instance. So, you do the manufacturing process, you carry out the manufacturing process, and then you carry out the heat treatment to change the structure. So, basically the processing route and structure finally gets generated from the process. So, first you start with the performance, and then you arrive at the structure and the corresponding process to arrive at that structure and the process. So, this is what we mean by materials development, meaning you start with the performance and then you come back. On the other hand, if you have a material which has got a certain structure, let us say you have, let us say Inconel as a material, which is a high temperature material, it has got very good properties in terms of low DBTT, etc., being a face centered cubic material. So, it has very low DBTT, and it is also able to withstand relatively high temperatures. So, my choice of material will depend upon the structure, basically the face centered cubic structure. I have the process to obtain it, and based on that I get number of properties. Now, if I have to modify the properties of nickel. For example, I add a number of alloying elements so that the properties get enhanced or properties get modified, and then I expect certain degree of performance from that material. So, I select a material and then I look at the its utility under different conditions. Usually what happens is when you select a material, you start with performance and then you go backwards to the properties, to structure and the corresponding process that will help you to develop that material. So, usually we start with the design part of it. So, when you have product design, then you have material selection for the product. In fact, many times material selection takes place first. For example, you want to make a car, you want to make a car body, for instance, you would select the material, whether it should be aluminum or whether it should be steel or whether it should be a hybrid or say multi material construction, and then correspondingly decide on the properties and the corresponding structure and the process. So, basically these are the steps which we take in material development and selection. Now, the need for new materials has always been there. For instance, natural materials do not suffice for all conditions because our requirements, the needs have been changing and these needs have been increasingly challenging. So, the naturally occurring materials do not suffice anymore. So, even if you alloy a material with many other alloying elements, for instance, you have iron alloyed with a number of other elements like carbon, chromium, nickel, etc., still it does not suffice anymore. So, with increasing severity of working conditions, increasing demand on the material properties, we need to develop new materials. So, we have artificial materials like composites, which are a mixture of again naturally occurring materials and artificial materials like polymers and fibers or polymers and so maybe could be glass fibers, carbon fibers and so on. So, you have a mixture of these naturally occurring as well as artificial materials to generate the kind of properties which you want. Well, having said that, not every application requires a radically new material. One can always say that I want this kind of material within the framework. Maybe I am not able to visualize that right away, but then due to materials informatics, I can go through the enormous amount of data, that is what I call the data mining. I have plenty of data which is available with me on different materials, their behavior, their mechanical properties, physical properties, density. So, I have a description of a material that will suit my purpose. So, not a single material, no single material might be able to fit the bill as it is called, but then I might have to therefore combine the properties of a number of materials and I might want to mine the data of several materials so that I can find out which are the nearest candidate materials which can possibly be used, and then which are the materials which could be possibly be combined together so that I can fulfill my wishes. Now, there is another issue here. There are many laws, many empirical laws which we have studied so far. So, many of these empirical laws like Hume-Rothery rules for instance for alloy formation. Now, many times we see that these rules are not exactly valid under all conditions. Basically, these are empirical rules and they are valid under most conditions. So, now if we extract these rules, if we extract information or if we conclude on the behavior of the material under different conditions based on analysis of data, then we will be able to get the exact behavior of the material rather than the empiricism that is associated with it. We will see how material informatics changes the rules which have been arrived at based on empirical considerations. So, what I am therefore driving at is that we need to mine data in order to get existent or get candidate materials which can possibly be used for a new application. We need to understand how function emerges from assembling appropriate atoms in the right way, as well as how to precisely make the design material with design properties. So, what I can possibly do is, let us say we have a number of Bravais lattices, we have 14 Bravais lattices. Now, I can wonder why I cannot have a crazy looking lattice which might not be among those 14 lattices which you might have been taught, but then is that lattice feasible, is that lattice configuration stable? Now, what is the atomic radius, what is the electronegativity of the atom, what are the kind of physical properties which could possibly be needed, so that I can assemble a number of atoms into that lattice configuration. So, I do not know how that kind of lattice configuration will behave, how it will remain stable, or whether it will remain stable at all, how to bring it into existence. I just do not know a priori, because I am trying to look at a material which is non-existent. I am trying to find a new material with a completely new lattice configuration, right. So, if I am trying to get a completely new crystallographic configuration, then I need to do many conceptual experiments. So, what I do is, let us say I decide on a crazy looking lattice configuration, then I check whether it is thermodynamically feasible to have it that way or not. Then, having done that, okay, if it is indeed stable, how will it respond to different parameters like temperature, for instance, or application of mechanical force, for instance. So, under different conditions, what is the predicted behavior of it, and then will it still remain stable under these conditions. The stability will depend on a combination of different parameters. Once I am assured of that, then I can assemble many of these lattices together, these new lattices together, and then check what kind of properties, what are the property, what is the magnitude of property which I get, how much is the yield strength, how much is the tensile strength, how much is the ductility, how much is the creep strength, how much is the fatigue strength, how much is the corrosion resistance. So, I can try to predict again, because I have still not built the material yet, I am still at a conceptual stage. So, what I do is that I try to build a model, I try to analyze based on laws of physics these behaviors, and then try to predict what kind of behavior, what kind of strength, how the material will behave at under different conditions. So, these predictions are made, and then after these predictions are made, if it is satisfactory for me that yes, okay, I can expect the kind of behavior I am looking for, then I start looking at how I can synthesize the material, from where do I get those atoms, how do I put the lattice together, and how do I synthesize the material. So, again I need to therefore analyze the manufacturing route basically, and then get to the business of manufacturing that material and then testing it out, because everything needs verification. So, my expectation so far is based on analytical methods, but now having made the material, I need to verify, right. So, we use mathematical and statistical methods to extract patterns that can be leveraged for material discovery, design and optimization. So, what I talked about so far is right from atomistic approach. My expectation or my intuitive lattice structure, which might be innovative, it might be different from the lattice structures which exist, and then I predict the properties, the behavior of the material, etc., and then verify it. Alternately, what you can do is you can have mathematical and statistical methods which can extract patterns so that you can generally get an idea about which material can possibly get close to what you want to do, and so you can have these statistical methods and mathematical methods to have material discovery, design and optimization. So, you are essentially trying to find a pin from a haystack. So, there is plenty of data that is available, and which is the haystack, and then you want to find the pin that is your requirement. So, something that fits your bill from a big body of data which conceals what you want, right. So, the discovery and optimization of materials is naturally time consuming, labor intensive, complex and expensive, and therefore, you make it feasible by using computational power. So, whatever I am trying to describe to you is a need which can be either realized based on doing the theoretical work first, like you believe that certain material can exist based on the established theoretical principles of physics, and then you synthesize it, verify it, and then and check whether the models you had used or the analysis which you had made is realistic or not. Product designers need precise information on materials, functional performance and environmental impact. So, if you want to, so now if you look at the product design aspect of it, if you want to translate this from, let us say, atomistic level to a product design or application to a product, then I know that for a product I need certain properties, and then I work backwards to translate the requirements of the product into material properties. These material properties get translated into structure, what kind of structure that could possibly serve the purpose. Now, if it turns out that, well, I do data mining, I try to find out a structure, I try to find out a material that will have those properties, then well and good. In fact, I can use computational power to browse through a big body of data and get the precise alloy, the precise chemical composition of the alloy that will help me. On the other hand, I can also say that, okay, there is no material which exactly fits my bill, so I will synthesize a new material, and I can get some clues based on this data mining. I can design the new material around the principles which are indicated by the data. So, we have the 4 paradigms of science. First is empirical science. So, you have the data based on what is available, because empirical work or experimental work, empirical science can be done based on whatever is available. Then you can go to model based theoretical science, where you can extend the principles to the realm of unknown unknown materials, for example, and then you can look at the you can extend this further to using computational science or simulations to check whether the let us say the crazy lattice which I was talking to you about would be feasible or not, or how it will behave based on such simulations. So, initially you have based on laws of thermodynamics inspected the feasibility of the existence of that crazy lattice, which I might have devised as the 15th or 16th lattice structure beyond what is available today, and then I check with computational science and simulations, and then I use predictive analytics and so on in order to find out whether I can really get to that particular property levels or not. Now, if we do not use informatics, meaning if we do not use machine learning and those types of and these types of fast methods, we will not be able to achieve the final goal in a very short period of time. So, the idea here is that to speed up this material discovery. Material discovery using these 4 steps will anyway happen but then it will take a long time unless we use the principles or we use the tools pertaining to the data in material informatics. So, what we do is that material informatics can generate inverse models for optimization and design. So, you maximize a property such that structure follows certain constraints. So, what you do is that you either start from the property. So, now this is processing, structure, property and performance. So, you have performance in mind and then you translate that into properties, and properties have to be arrived at through structure. Now, this structure means not only microstructure, but also the crystal structure, crystallographic structure, crystallographic orientations, and then you would have in that the structure of the grain, number of phases present, and therefore, the corresponding processing conditions would be established once you have determined what kind of structure, what kind of phases should be present in the microstructure, so as to achieve the properties and the performance. For example, if you want to have a fine grain size, okay, if you want to have fine grain, so a performance, for example, is performance means very high strength, high yield strength is required. The corresponding, so performance means high hardness, wear resistance, strength is required, okay, durability is required. So, the corresponding property would be that high yield strength is high yield strength, high UTS, large amount of hardness, hardenability or work hardening rate, etc. is needed. So, I have translated the performance requirement into property requirement, and for that the structural requirement would be a fine grain size. I want to get a fine grain size, right. So, if I get a fine grain size, you know that Hall Page relation correlates grain size with the yield strength of the material, and larger is the yield strength, usually larger will be the tensile strength as well. So, I will then have I will then look for a fine grain size. I will also look for phases in the material which are ductile in nature, meaning which do not impede ductility. So, we have seen in the example of cast iron about how some of the white cast iron when annealed gives you say malleable or ductile cast iron, right. So, basically you are changing the structure so as to get the specific properties. So, when you want to change the structure, naturally the processing comes into play, and then you generate new processes to get the right kind of structure. Now, all this has to be done computationally or using what we call as materials informatics. So, that is what I have given you a very simple example, but then the performance gets translated into the processing conditions using intelligent programs or intelligent means. So, if I take a structure, for example, if I take a microstructure, then I can correlate the feature of the microstructure with the performance directly through a neural network or some intelligent means, or basically through some machine learning models. Similarly, if I have a chemical composition of the material, because chemical composition is important for me to get a fine grain structure, right. It is not just the processing conditions, but then it is a chemical composition and the processing conditions which will determine the microstructure for me. Now, if I have a correlation between the processing conditions and the grain size, for example, linked through a black box type of a machine learning tool, then I can predict based on the data, which is the chemical composition, the working conditions, like I might have done some mechanical working on it. So, the grain refiners might have been added. So, whatever I might have done to get a fine grain size. So, these processing conditions or process parameters are listed out, and then it is correlated with the expected grain size. So, for instance, when we talked about melt spinning to get amorphous metals, we talked about a cooling rate. For instance, I have if I want the structure to have extremely fine grain or amorphous structure, then I will have another parameter called as cooling rate. So, in addition to chemical composition, I will have a parameter of cooling rate. So, I get an amorphous structure which will give me certain properties, and then so by virtue of amorphous structure I can get very high amount of ductility under superplastic conditions because of the very fine grain size or amorphous state, and then thereby I can get a certain degree of performance from that from the product I make using that particular material. So, this is how I translate performance into structure and processing conditions. Similarly, we can move in the forward direction, meaning you have scientific relationships of cause and effect. So, you have the processing conditions, like for example, you add, let us say you want to determine the chemical composition, then you add, let us say, molybdenum for creep resistance. So, you have cause and effect. You know, molybdenum increases the creep resistance. So, you add those materials, you need chromium to increase the corrosion resistance. So, you add those, then you get the proper structure of the microstructure of the material, the properties, and so you know the scientific relationship of cause and effect, and therefore you build them, each one of them in, and then get to the properties and hence the performance. So, you start with the chemical composition, processing conditions to get the structure. The structure will give you the properties, and the properties will give you the performance. So, you can start with the basis as scientific relationships of cause and effect. So, these are called as forward models and which can be generated using material informatics for predictive analysis. So, you have a property as a function of processing, composition and structure. So, this is what is shown, whatever I spoke about is shown in this picture, where you have the strength coming from different sources at different length scales. So, right from quantum length scale to atomistic to mesoscale continuum, and then you at this point, once you get a continuum or you get a material lattice, then you can I mean, you have a monolithic material that is possible or continuous material that is possible, and then you have a product made out of it. So, at this point you select the material, right, you select the material where it exists as a continuum, and then you make the part out of it, assemble it, and then the system takes off. So, again here you have cause effect analysis methods, and if you go backwards, you have goal oriented design method, because your goal is to fly, and then for that you need a engine which is able to generate certain amount of power, and so materials which will withstand certain temperatures at certain pressures, right, and those materials have to be chosen. So, your turbine blades or turbine discs and many other high temperature parts, the combustor parts and so on, will have to be chosen to be assembled together. So, now you have set a goal for yourself and you are working backwards so that you can design the material. So, you have to move down in atomic scale, so that your source of strength, namely source of strength comes from all levels. I mean, you need to ensure strength at all levels as you go down the length scale. So, this summarizes whatever I have talked so far. You have a component, and then so this is basically a cast component, and then you are generating a microstructure. So, you need certain properties of the material, and then you have a certain manufacturing process that gives you the microstructure, macrostructure. That macrostructure translates into microstructure. So, you know what are the features of the microstructure you want, which are the features you do not want, and accordingly you will set your processing conditions. So, you are going down from the final component down towards the microstructure, and the means of achieving those microstructural features including the nanostructural features like dislocations and grain boundaries and so on. So, this is in short the sum and substance of whatever we have been discussing. So, now we have different tools at different levels. So, we have been talking about different length scales, and we have different tools for measuring as well as measuring quantities as well as modeling them under different length scales. For example, at atomic scale or at the lowest scale length scale, we have DFT density function theory or molecular dynamics as the modeling tools, and we have atomic force microscopy or high resolution transmission electron microscopy. So, there are several such techniques which are available at atomic level or angstrom level, angstrom length scales. So, we have atomic scale which is here, and these are the techniques available at atomic scale. At single crystal scale, so now we are going from atom to single crystal, we have molecular dynamics and as the simulation method, and that is analytical method, and then you have TEM and tomography as measuring that is experimental tools. Then you have phase field modeling and crystal plasticity finite element method for at polycrystalline scale. So, here we were at single crystal scale, now here we are talking about polycrystalline scale, and then you have in situ TEM, SEM and EBSD for experimental purpose. So, at each level of component scale, we have modeling tools as well as experimental tools, but then we need to bridge the gap. So, what bridges the gap is the materials informatics, because everything comes under a single umbrella. So, what we do is that we translate the results from these mechanical properties to the kinds of properties which we would like to see here, to the results which we like to see there, and then to the outcomes like arrangement of atoms, for example, that we would like to see through the AFM and so on. Now, this is made possible by availability of in service data, like for example, if you want to fix the properties of different materials being used in an aero engine, you would like to know what are the kind of temperatures, what are the kind of pressures which are being developed, then you need sensors to be present everywhere. And once the sensors are present, they will sense these the parameters developing inside in the engine, in the working part of a product, and you will communicate those results, those signals, and then process those signals, take online decisions or real time decisions, and have an actuator to work so that the temperature can be controlled or pressure can be controlled. And then having sensed these temperatures and pressures, you would also start looking at how things can be improved. You can use the same data for finding materials which can go beyond what is available or what is feasible today. So, we have information computation, communication technologies including big data analysis, artificial intelligence algorithms, data mining, machine learning, industrial IoT, Internet of Things. So, high performance computing, cloud computing, these are all available, and these provide opportunities for material design and material selection based on functional performance requirements. So, if one is to do this manually, it will take hell of a time, whereas if one does this analysis using computational tools, the so called big data, the huge body of data which will take years for a person to analyze, can get analyzed within hours. So, that is what is important. So, what was not feasible earlier, material creation, new material creation, for example, the visualization of how the material will behave, how the new structure which you might have proposed will work in service conditions can all be predicted using laws of physics when they are modeled into these different into different models at different length scales. So, material creation is facilitated by combinatorial material science, high throughput analytical techniques, and computational material science based on accurate electronic structure methods and materials property and failure prediction software tools. So, basically we need the experimental methods which we saw for verification, and we need the computational tools for prediction. So, we use computational tools in order to generate the theoretical feasibility of a given structure, theoretical feasibility of getting certain level of properties, feasibility of manufacturing that material using a manufacturing process. So, we analytically do everything, but then at every stage we need to verify whether that structure is indeed being obtained using those manufacturing methods or not. So, basically we need to therefore use both analytical methods as well as experimental methods, and then all the data that is generated, both success as well as failure, gets accumulated or keeps on growing. So, that body of the data keeps on growing, because basically what you get is experience, right. So, even if you do not get to the final point of generating the properties, all effort you would have made in analytically visualizing certain crystal structure and the predicted properties, etc., because everything is subject to assumptions, and so even if you do not get to the final product, still the experience that that is generated, the data that is generated, after all experience is data. So, that also gets incorporated. So, what kind of data would give you success, what kind of data would give you failure gets accumulated, and these AI ML tools will correlate situations which generates success with the parameters which are the metrics of success. So, for instance, I will say that the ductility of the material should be let us say at least 50%, the fracture toughness should be so much, the ductile brittle transition should be so much. So, there are number of requirements I give. So, these requirements are metrics of success. If I can get superior properties to this, I would have succeeded. By having different chemical composition, processing conditions, etc., I can correlate the big set of material properties, the chemical composition, the processing conditions with the material properties obtained using a black box type of algorithm like AI algorithm or data mining or machine learning algorithms, right. I can say that these are, see, many times, I mean in all our theoretical study we take only the major elements, we do not take the tramp elements and many other elements which do have an effect on the final performance. We just say that they should be less than so much, or but then now is an opportunity to capture the effect of the variations in the material properties, the material mechanical behavior that these elements could possibly introduce. So, now you have a big list of these elements which are possibly present in the metal, let us say steel, and then you have the processing route starting with the melting temperature, pouring temperature, hot rolling temperature, finishing temperature, coiling temperature, and so many other things which are involved. So, it is a big list of data. Each parameter shows a variation, and therefore, there is going to be variation in the properties that are obtainable. Now, I have a body of data giving me a set of parameters correlated with the output, namely the fracture toughness, the ductility, the strength, and so on. So, now I can therefore correlate the processing parameters with the properties obtainable, right. So even if I fail to obtain the properties I expect, I get properties inferior to what I had expected, still I know that a certain set of data gives me inferior properties. So this data set gets added to my knowledge, to my knowledge base. So I call it as knowledge base because now it is not just data, it is not just information, it is knowledge, because it tells me that this kind of this data set gives rise to a inferior result or a failure result, whereas another data set I might have might give me success. So I can delineate conditions giving me success from those giving failure. So basically this availability of in service data helps a lot, and one needs to therefore be able to use it for construction of new materials and for arriving at predictions of how materials will behave, or your new material synthesized would behave. Will it be adequate or will it be inadequate? So now this is an illustration of how we can draw inferences, statistical inferences from the data. That is, we have lot of data that is coming from the material. We have sensors sensing the various attributes of the material, and so now we have Hume-Rothery rules which we know of, right. So you have empirically known rules as atomic size factor is one of the rules which governs whether an alloy will be formed or not, whether metal A will dissolve in metal B or not, whether substitutional solid solution will form or not, right. So now these are empirically known rules. Now what we observe is that in reality is that the valence electron factor and atomic size factor are dominant, the electrochemical factors are less dominant. So although there are 4 Hume-Rothery rules, all the rules may not be equally applicable. So in some cases you might still get alloying, you might still get solubility of A in B in spite of a couple of rules being violated or not strictly being followed. So that is because there are certain rules which are dominant and certain factors which are not so dominant, or which are kind of less dominant or recessive, shall we say, right. Similarly, for another structure type, you have valence and electron factor and atomic size factor which need to be satisfied, but then here the valence electron factor and atomic size factor are dominant. So these are the dominant factors. The electrochemical factors are less significant, right. So under different conditions, for different kinds of compound, for different kinds of structures, the dominance, the relative dominance of these factors keeps on changing, but that is something which we cannot infer based on theory, because our theoretical understanding, the rules of physics are based on certain assumptions we make, whereas the data that is coming from in service conditions has no assumptions, it is all reality. So that is why you take hard data from in service conditions, and then you have, let us say, then you extract information, whatever information you would like to extract from that data. So now there are no assumptions involved. So when we approach a problem, when we try to construct a new material starting with atomistic simulations and atomistic theories, atomistic rules, as we see here, we are bogged down by assumptions, and therefore our predictions will not generally match with reality. So what we need to do is that extract the material behavior, extract the rules from data, so from big data. So that is what we do. So we have the material behavior in the form of data, and then we extract the constitutive equations from there, right. And then similarly we use this data for statistical learning, and then we build predictive models, or we can classify success data pertaining to success, that is conditions of manufacturing which would lead to success from those which would lead to failure. So, by now you would have understood why material informatics is needed, because it provides us a web based platform and data infrastructure with which it is easy to search for specific materials, information from anywhere in the world and at any time. So, I have a large amount of body of material. Let us say you have a big handbook, there is a handbook of materials which is this thick, and now if you have to rummage all the pages to find out the material which will fit your property requirements, well, it might not be practically feasible. So, instead, if you have a web based platform and the data infrastructure, there is a huge database which is available on the web, you have a web based platform to search for which materials or which kind of alloys will suit my application, then I can get that information in a very short period of time. So, that is just one part of it. It also supports data generation. So, basically it supports data generation, acquisition, storage. Data acquisition can happen through sensors which might be positioned at appropriate locations to measure a number of parameters. So, you can generate data based on simulations. So, you can have the many sources of data. It could be either experimental data, it could be based on analytical sources. So, analytical data would mean that there are certain assumptions which are used, but real life data which are acquired from sensors or transducers are real life data, but then that would also be subject to data inaccuracies due to noise. So, whether it is generated data or acquired data, both will have their own downsides or sources of inaccuracy. Generated data will be inaccurate because you have assumptions which stand between reality, I mean between you and reality. The acquired data using sensors would have limitations of the sensors, drift in the sensors due to temperature or whatever, the sensor getting loaded and things like that, as well as noise. So, interference of different signals, noise, etc. will be another issue when you acquire data. Data storage, mining, processing, management and visualization is all possible using material informatics. It involves generating reliable data. So, since everything is data driven, because you are going to use data for extracting laws of nature from the data, instead of proposing laws based on the established rules of physics. Basically, you extend the existing rules of physics to new domains. Instead of doing that, you extract the rules which are prevalent in nature, laws of nature, based on the data that you get. So, by analyzing a large amount of data, a voluminous data, you are able to establish certain rules which seem to be followed in nature, right. So, this is typically for let us say predicting the climate or predicting the weather, for instance, right, because you have plenty of data over the years, and then how the monsoon patterns will occur in different parts of the country, where the rainfall will be more than normal, less than normal. Now, in the olden days, the data used to be inaccurate, meaning maybe it was not adequate. So, predictions were also off, but then with time that data also got accumulated, that data was also being used to train the models, and therefore, the result is now today the predictions are far more accurate than the previous predictions. So, basically when we keep on collecting data over a period of time, data coming from different sources, the behavior is extracted from the data, the behavior of the laws of nature are extracted from the data, and that makes things more realistic. So, reliable data is very important here, and data on effect of material changes, namely structure and properties and performance during fabrication of products and service life of the product also. So, there are data required from various angles, like you need data with regard to manufacturing, you need data for design, you need data for material selection. So, for each and every objective of yours, a different data set is needed, and that needs to be analyzed. Similarly, recyclability of the material at the end of life. So, all this taken together forms an enormous amount of data, but then the materials informatics has the capability of bringing this in under one single umbrella or one single platform. We know that, I mean, based on our discussion so far, data is highly heterogeneous and it comes from several sources in different formats. So, it can come from different kinds of sensors working on different kinds of principles, right. So, temperature sensor can work on different principles. It can so the accuracy of each sensor is each kind of sensor is going to be different. So, basically each source of data has its own sources of inaccuracy, own sources of noise. So that is why data is heterogeneous. So, it is not like a one-to-one correspondence that, so 2 plus 2 equal to 4 is not going to happen because of the noise in the data. So, under the same conditions you can have different response. So, for the same apparently the same set of parameters, you may have some deviation in the output as you analyze the data. So, the data is heterogeneous and comes from diverse sources in diverse formats. Now, we have some analytical tools in materials informatics. So, I will just briefly go over one major tool, which is CalFAD, which is calculation of phase diagrams, which are so fundamental to our understanding of phase transformations as well as heat treatments. So, it captures both experimental and computational data related with thermodynamics, kinetics of diffusion, molar volume, elastic properties, electrical conductivity and so on. And then here also machine learning and data mining play an essential role in emerging materials informatics, because it can now correlate. So, CalFAD can generate data analytically, what kind of microstructures will result from what kind of chemical composition at what temperatures, at what cooling rates and so on. And then this correlation is captured by the machine learning and data mining algorithms, and so that gives us a faster correlation between the conditions of manufacture, the chemical composition and the corresponding microstructure that is obtained. And then if you can correlate the microstructural features with the properties obtained, again through a similar ML tool, it will be very easy to go from the chemical composition to chemical composition and processing conditions to the final performance predictions very efficiently. Now, we therefore see the various attributes of the big data and fusion of data across multi-scale models. So, we have 4 attributes of big data. One is veracity, variety, velocity and volume. So, you have a big variation in terms of reference data, which is absolutely certain, reliable, and to data which has got very high levels of uncertainty. So, this is these are the 2 extremes of data veracity. Similarly, you have data variety in the form of single scale to multi scale. You have difference in velocities from static to dynamic data. So, static data would mean it does not change with time, but dynamic data changes very rapidly with time. So, velocity of data, velocity with which data changes. Similarly, volume of data can range from terabytes to zettabytes. So, the volume of data can also have a big range. So, these are the 4 parameters, attributes of big data which can vary from one end to the other. Here you have the fusion of data over multi-scale models. So, you have experimental data being used. So, because experimental data is the real life data, and that gives I mean that is used for first principle calculations, and then it gives rise to kinetic data, interfacial energies. So, basically you infer these parameters from this data, and then this when given to these softwares like CalFAD will generate more data pertaining to bulk thermodynamic database and so on, and kinetic database. So, this CalFAD will give you the many parameters here, which when fed to phase field simulation will be able to predict the proper microstructure here, properties of elasticity and plasticity of different phases, and then this in turn will be able to predict the what kind of properties and what kind of mechanical behavior the material will have at the time of loading. Again, you have experimental data which is available on a macroscopic scale for verification. So, basically you need experiments for initially starting the first principle calculations, and then we also need experimental data for verification of the predictions which are based on these analytical tools which have been used en route. So, to summarize whatever we have said so far, we have a knowledge discovery workflow which starts with a heterogeneous material database, and then we go towards the process structure, property and performance correlation, and that is stored as a knowledge. So, knowledge is essentially a linkage between these 4 parameters. So, information would mean only processing conditions, information would mean only properties, information would mean only performance condition, performance parameters and so on, but knowledge would mean these linkage between these 4. So, we start with heterogeneous databases. You have data coming from experiments, simulations, DFT, molecular dynamics, chemical composition, processing, structure, properties, performance, papers, reports and so on. So, you have new data coming in which is always going to get added, right, based on your subsequent modeling and simulations. So, you have therefore data getting updated continuously. Then you have data extraction and pre-processing, so that you have consistent data consistent with your objective being mined. So, you have data extraction. Then you have data reduction, because you have a number of parameters, you have large number of parameters which you have extracted as being relevant to the problem, but now you need to find out those which are the major influencing parameters. So, those parameters which can explain the performance of the material the most only need to be considered, because you do not want minor contributions, you would like to capture the major effects. So, that is why you need data reduction, otherwise the problem will become extremely complicated, extremely large, the data set itself will become extremely large. So, you have data reduction by reducing the number of parameters, by identifying only those which influence the final outcome, namely the performance, to the maximum extent. So, you would do data reduction and selection, and subsequently you would use that reduced data, meaning the parameters which mainly influence the performance in the modeling, and you have relationship mining taking place. So, you have similar materials which would foot the bill. So, you would identify different materials or maybe similar material basically, which would cater to your requirements based on modeling and relationship mining. So, you have reduced the number of parameters which would influence the performance, and then you model these parameters to check which of the materials of so you use material properties, only those properties which are important from the performance point of view, and then find out which materials are similar, or what is a set of candidate materials which will help you. Then you have evaluation, understanding of the having chosen the materials, you would like to understand how the material will work to fulfill your objectives. So you have evaluation, understanding and feedback. So supposing it turns out to be a failure, I mean you have based on your models you find similar materials, but not all of them in spite of being similar seem to be working out favorably. Then you give a feedback so that you again go back to the data extraction, and then you extract more data so that the at the evaluation stage or the property prediction stage you have a material that will suffice your requirements, or which will fulfill your requirements. So this way you have the properties, and then you discover new materials which will be able to fulfill your objective. So basically what you are doing is you are coming from a heterogeneous materials database and going to new material discovery and storing the processing, structure, properties and performance of the new material in the form of knowledge. So this knowledge is finally generated, and again this gets added to the body of knowledge, or basically the data which you had started with earlier. Now typically in material informatics our algorithms are machine learning algorithms, but then there are 4 main algorithms, namely dimensionality reduction, meaning number of parameters being reduced, what we saw here. Data reduction basically is essentially dimensionality reduction, regression, clustering and artificial neural network. So these are the 4 major algorithms of machine learning. Deep learning is also one more algorithm which is which would be used for materials informatics. So now clustering is meant for outlier detection, and it is a great challenge in machine learning on how to choose an optimal algorithm with appropriate fitting of available data without overfitting or underfitting. So this is a very important challenge which needs, so the algorithm chosen has to be has to be carefully chosen. So you have to again go with several algorithms and choose the best of them. So here is an illustration of classification of microstructures. So you have reduced the data into 2 principal components. So you have principal component analysis, which explains the orientation of these elliptical precipitates. So in some cases it is vertical, under certain conditions they are horizontal, a few other conditions they are randomly oriented. So you have 2 principal components correlated with each other, and so under for certain values of component 1 and component 2 the orientation is horizontal, at others it is vertical, and few others it is random. So you can establish therefore reduced order representation of microstructures and the conditions under which they can be obtained. So for this you need what is called a descriptor. So now I am getting into the jargon. We have already seen what a descriptor means. Basically we were talking about different parameters like chemical composition or mechanical properties, grain size, all these are called as descriptors, right. So descriptors are called as features or attributors as well, and in metal forming descriptors could be raw material composition, microstructure, shape, size of raw material and metal forming conditions. So it could be temperature, it could be force, it could be strain rate and so on. So descriptors are decisive factors in the construction of mechanism independent correlations between targeted properties and descriptors. So now we are talking about machine learning algorithm which does not care for a phenomenological events taking place. So it is not concerned about physics, of the problem. So, what we do is that you have machine independent, mechanism independent correlation is established like a black box. So, you have descriptors which determine the final outcome. So, we correlate the descriptors with the final outcome, and these are mechanism independent correlations, right. And so, these descriptors guide material design and discovery. So, I can say that okay, if I combine so many metals together, I get this kind of properties. So, then basically I do data mining, I do the correlation between the descriptors which are essentially properties of these different 4 or 5 materials which I might choose, and then I correlate that with the targeted properties, right. So, like for example, high entropy material, I want to predict the properties of a high entropy material. I take 5 different materials, and then I design a particular high entropy material, and then so the descriptors will guide me to understand what kind of properties I can possibly get in the high entropy material by correlating the properties of these constituents with the properties obtained of the in the high entropy material. So, basically this is how I can discover more and more new materials using data mining and descriptors which are correlated with the outcomes. So, appropriate descriptors. So, it is important to select the appropriate descriptors, because you should be able to choose the descriptors which will influence the final outcome to the maximum extent. The mechanism based analysis of data is physics based data. So, descriptors are well defined and properties are explicitly or implicitly expressed using analytical expressions. That is what we are familiar with. We are familiar with the formulae correlating certain amount of the chemical composition with the strength of material. So, if you have a deterministic expression, a mechanism based expression, then this is called as mechanism based analysis of data. But then we need the descriptors based on a statistical model which will we need descriptors which will be able to correlate the input with the output accurately. So, a descriptor uniquely characterizes a material as well as property relevant elementary processes. So, these are basically the attributes of a descriptor, and number of descriptors should be as low as possible. So, that this is the whole crux of data reduction. So, you try to use as a few descriptors as possible, right. And determination of a descriptor must not involve calculations as intensive as those needed for the evaluation of the property to be predicted. So, descriptors could be intuitive in nature, or descriptors could be extracted from the data by analysis of the data, but that analysis of data should not involve intensive calculations. Now, we will see we have already seen the different sources of data, and then we will continue with this with the different approaches to the material informatics or new material design in the next lecture. Thank you.